Okay, I'm sending. Give me a second. The link is in the chat. Okay, so we are starting in exactly 4 minutes.
Esto es lo que la gente ve en YouTube ahora mismo. La ya. Ah, esa. Gracias.
Sí, ahorita ya estamos en vivo en YouTube. No, es cierto. Puedo poner una cuenta regresiva. A ver, vamos a ver. Mm, eh, no, estoy con el micrófono encendido. Okay, so good morning, everyone. I am Angel Mendez, president of OPTICA EPN, and today I want to thank you all for your presence today, especially to our panelists, Carmiña, Emilia, Jennifer, Carla, and also uh, Carolina, I'm sorry, um, who are outstanding researchers and whom we are honored to welcome today. I feel very honored that the third edition of this event has the presence of Jennifer Chacon, who initiated this event in 2022. So I hope you enjoy today and that you find each of these excellent women a great inspiration. So Anna, please continue, and thank you.
Well, good morning for everyone. Welcome to our Women in Science event. For the third consecutive year, the OPTICA chapter of the Escuela Politécnica Nacional is pleased to generate a space aimed at recognizing and promoting the active participation of women and girls in STEAM. We are grateful for the presence of the scientists who are with us today. Each of them is at different stages of their academic and professional careers. And the work has received national and international recognition. We hope that this variety of topics and perspectives will not only serve to highlight the important work of women in science, but also to encourage girls to pursue careers in STEAM. With no more to say, I present our first speaker. As Angel mentioned, she was the one that initiated this event in 2022, sorry. She is a very important part of this chapter, and now we have the honor to have her as our first speaker. Jennifer Chacon is part of the Millennium Institute of Astrophysics, and she is a PhD candidate. Since her childhood, reading, science, and dissemination have been her great fascination. Throughout her academic career, she has not only immersed herself in research, but also led and developed projects that seek to bring physics and astronomy closer to everyone. Please welcome Jennifer.
Hi, everyone. As Anna mentioned, I'm so honored to be here, especially because I was part of the student chapter like a couple years ago. And today, as a PhD candidate student, I'm going to talk about one of the areas that is really related with optics, which is astronomy. And my aim here is that you can see how this relation works and the fascinating world of astrophysics as well. So I'm going to share my presentation, and please let me know if everything is working well. If I have some problem, please feel free to stop me. So I'm going to talk about today of astrophysical transients, and we're going to discuss what are they. And here is a brief table of contents of my talk. Specifically going to talk about extragalactic transients. So specifically more about gamma ray bursts and fast X-ray transients and some telescopes we are using today to study them. And without further delay, let's start by defining what are these astrophysical transients. So transient, we can understand this term as fleeting, something like that, but we are basically referring to phenomena that change their brightness over a relatively short time. It could last like a fraction of a second to weeks, hours, or even years. So the physical phenomena that can cause these events can be really wide, and we can kind of classify their origin in galactic and extragalactic. Here we have some examples of the galactic ones: nova, M-dwarf, flares, variable stars, and the extragalactic supernovae, gamma ray bursts, active galactic nuclei, tidal disruption events, fast radio bursts, fast X-ray transients, and kilonovae. And we have a really large variety. But today my goal is to talk about some of the strange ones. But here I have some bias because for me the strange ones are the ones that I've been working with, and I am passionate about them, as you're going to see. So let's move on to why it's important to study these phenomena, because we can think about, these transients, extragalactic ones, are really far away of our galaxy, and why this can affect the everyday life, or why it is important to understand them. So I here give you a couple reasons, because the importance relates in the pathways that can lead to these events, and we can gain new insights in the stellar evolution, how because they are related to stellar evolution. Also, the energy that they release can stimulate and inhibit the formation of stars. So we have the physics here of the evolution of galaxies as well, and some of them can enrich the medium, the interstellar medium. So we finally have the chemical evolution of these transients. And we can use them as extragalactic distances rulers, such as supernova. I don't know if you are familiar, but in 2011, I think, the Nobel Prize was because of that, and the basically measure of the expansion of the universe, the H-naught. And they are really important also because they are connected to multi-messenger astrophysics, which is kind of a new field of how to do astrophysics. Most of astrophysics is based on the light that we receive in all the wavelengths, but we also can study phenomena with not only photons, but also with neutrinos, cosmic rays, and gravitational waves. And the high energy of these astrophysical transients, of some of these astrophysical transients, may allow us to study in these other messengers, basically. So now I'm going to mention briefly some of the extragalactic ones that are kind of interesting, that of course are interesting, but for me, there are others that are more interesting. So here we have some pretty images. Some are like in situ. The one that is kind of in situ is this one, the first one, and the other like representation of the other transients. So the first one is a supernova remnant. Of course, supernova are these dramatic explosions that take place during the final stages of a massive star. Once they were discovered, the classification scheme was based on the spectral lines, on the presence of hydrogen or no presence of hydrogen in the spectra. But I find that most physical mechanism to classify them is basically to understand the explosion mechanism. Here we have two ways of classifying them: the thermonuclear explosion, which are the type 1A, that are the ones that have the hydrogen in the spectra, and they are related to the explosion of a white dwarf. So we have a system here, a white dwarf, that is accreting mass from a massive star, and as this white dwarf reaches the Chandrasekhar limit, it will explode, okay? And the other one that is the core collapse mechanism of explosion are the most familiar for us, that is like in the final stages of the massive star, it will blow up, basically. So we have here supernova. And the other transient I'm going to talk is active galactic nuclei. So basically we have a supermassive black hole that is accreting mass in the center of a galaxy, And as is accreting mass is going to show this as some energetic flare. So basically, that's the active galactic nuclei. And another one, I don't know if you have heard, but it's this tidal disruption event, and is related to a star also that it passes through close to a supermassive black hole. So the part that is more close to the supermassive black hole is going to experience a force different than the part that is more away than of the supermassive black hole, and this is called the tidal force. So what is going to happen is that the star is going to be tidally disrupted as it orbits the supermassive black hole, and the mass that is going to fall is going to cause this energetic flare that can be in ultraviolet optical, also X-ray. And the last one I'm going to mention is the fast radio bursts that are so energetic, like 10 times stronger than our sun, and they could last in order of milliseconds. In 2007, they were first discovered in archival data, and we don't know much about them, but some of the channels that can produce these kind of bursts are these highly magnetized neutron stars that are called magnetars. But yeah, we are currently studying these interesting bursts. So let's move on to what is more interesting to me, that are these strange ones. And they are the gamma ray bursts and the fast X-ray transients. So here we have the gamma ray bursts that were discovered first in the 60s because in the context of the Cold War. USA basically launched these Vela satellites into space to spy the nuclear essays. So what they found was that isotropically in the space, in all the directions, they were receiving these gamma signals. Here we have a plot of the galactic plane, and these points are these gamma ray bursts detected with the sweepback burst array telescope that is orbiting since 2004. It's really interesting to study gamma ray bursts because they are connected with multi-messenger astrophysics in this form. So in 2017, we detected the gravitational wave 170817. And this gravitational wave was because two neutron stars were coalescing and then finally merging. So 1.7 seconds after this gravitational wave event, we detected the gamma ray burst. And also we detected a kilonova, which is another transient in optical that is related to these kind of events of the dying of two compact objects. And the thing is that it was one of the, of course, the one replies in 2017, I think, was given to the people that study this. So we have that is a powerful tool to understand the physics in the most extreme form, because we don't know much about neutron stars, but if we have information of them colliding, we can understand a bit more, and maybe to in the future find the equation of the state and so on. And the work I did here in gamma ray bursts was to identify the peculiar ones, because currently we have this canonical classification. We can see here the short and long. We call short those that last less than 2 seconds in duration, and those that last longer than those 2 seconds, we call them long. And the association in the canonical classification is that those that are short are related to neutron star merger plus a kilonova, and those that are long are related to a massive star and a supernova. So gamma ray bursts are also produced because of the dying of a massive star that goes supernova. But not all the massive stars, the ones that are the Wolf-Rayet, a really specific kind of a massive star. So what I did was to analyze the third sweet bath gamma ray burst catalog that contained this number of gamma ray bursts. We made a sample of them, those that had redshift, because redshift gave us a sense of the distance, and then we can compute some other properties to identify those that were short in duration, but we wanted to understand if the other features maybe tell us that they are related not with a neutron star, but with a supernova. So that's basically what I did. We found 4, and some of the students there at Escuela Politécnica Nacional are working in those to understand it a bit more. And currently, I am here working with fast X-ray transients. They are more mysterious than gamma ray bursts because in the last 20 years, they are being discovered also in archival data. And the thing is that we can understand them at flashes of X-ray emission with duration from a few minutes to hours. And because of this satellite that it's called Chandra, we have a lot of data mostly from these events. And it's difficult to identify a multi-wavelength counterpart after the initial detection because, as I said, we found them in archival data. So in order to pinpoint the telescopes and maybe to see the host galaxy, and with the host galaxy to understand...
¿Qué están saliendo de clases? Sí. Vamos a mi estimado.
Oh, I think someone was getting
Yeah,
back.
Sorry, Jen. You have like 1 minute.
Okay.
Sorry.
As I was telling you, the important thing with these transients is to not only have this, I don't know, with Chandra we can have the X-ray signal, but what are going to give us more information is the optical signal. So we need to find the host galaxy of these events. So that's why the multi-wavelength studies in optical, near-infrared, ultraviolet are going to be really important in this kind of studies of transients. And here we have some papers from 2022 and 2023 from Jonathan Quirola, who was also a student on Escuela Politécnica Nacional, and he is now a PhD student from my university, Universidad Católica de Chile. And he found around more than 20 FXTs, and the current sample is about 40 of them. So the physical mechanisms that can produce a flare of X-rays are these varied. We have here stochastic outbursts in X-ray binaries, the short breakouts of a Corcola supernova, of axis gamma ray bursts, also a tidal disruption event, but a really specific one with a white dwarf and an intermediate mass black hole, and the mergers of binary neutron stars. But how to know which channel is like the one that is producing these events? We need to finally find the X-ray luminosity. And here we have some ranges between which channel could be possible. So basically, by finding this, we can understand, okay, yeah, it's more possible that this event comes from, I don't know, merges from binary neutron star, but for that we need more data and of course the multi-wavelength studies. And that's what I come from this telescope slide.
I'm sorry to interrupt you, but your time is over, so sorry.
Yeah, I'm going to conclude quickly because this is, yeah. We have optical and near-infrared. That's what I was doing from these telescope Gemini and Gimos that are here in Chile. And the last thing I'm going to tell you is that quickly we have here a really important telescope that is the LSST. Here we have an image that is shocking because it's one of the lenses of the camera. Of LSST is going to be the most large telescope known, and the field of view is huge. I think the angular size comparison of the moon you can see here is quite huge. So for those that were like, astronomy is fun, but they have a lot of optics in it. So basically that's what I was going to tell you today. Here is a brief summary, and thank you so much. You can write me questions or whatever. Here are my socials. Thank you.
Okay, thank you very much, Jen. We have one question, but the last thing you said, I think it answered it partially. Well, most of it. So thank you very much. For time issues, we are not having any more questions, but it was a very interesting talk. As we said, we thank you very much for your presence here today. And we're going with our next speaker. She is Carolina Salgado, master's student in applied physics at the University of Sao Paulo. Her photonics research began during her second year of biomolecular physics bachelor's program at the Sao Carlos Institute of Physics. Additionally, she has a special studies certificate in biomedical engineering. During her final year, she participated in the OPTICA's student leadership. Her research is centered on the photophysical characterization of organic molecules, with a focus on both linear and nonlinear spectroscopic techniques. She is going to tell us about the methodology for determining the triplet quantum yield of photosensitizers molecules. Welcome, Carolina. We're very pleased to have you today here.
Thank you for inviting me and for all those here present. I'm just gonna share the screen. Okay.
Carolina, your sound is like very low.
Oh, really? Okay, so is this little higher? I don't know.
It's still a little low.
Okay, I'm gonna just.
We can hear you very well. Sorry.
Sorry, just a second. I'm gonna change the. Oops,
Okay.
sorry. I'm gonna change the. The speaker to the. It is better?
Um,
Can you guys hear me like that?
yes, we can hear you better. Continue.
Okay.
Welcome.
Sorry. So today I'll present to you some of our research where I determined the triplet formation quantum yield of photosynthesizers. But first, I'll talk a little bit about me. I already have my bachelor in biomolecular physics at the University of São Paulo, São Carlos Institute of Physics, and currently I'm pursuing my master's in applied physics. I started working there in mid-pandemic with the photonics group, and I had the opportunity to actually be present in the student union. I actually founded the Girls from the Physics with other girls, which meant to be a safe space for girls and like to try to get into disguise of the subjects. And I organized the physics symposium at my university, and actually I'm the current president of the USP of student chapter. And about my research, I, since the beginning, started working with porphyrin molecules, characterizing them. First, I characterized the ones with fluoride ligands, which resulted in a published article. I actually got to work with tetraphenyl porphyrins now with Chopin ligands, which resulted in the final work for my course. And these both works actually got to be presented in an international conference like UFO and FIO from USA. So the motivation to work with this kind of molecules are the applications of it. We have the photodynamic therapy, which is a very interesting application because we can kill cell cancers and other microorganisms through the generation of cycloreduction and other reactive species of oxygen by just irradiating light as some photosynthesizer molecules, so some molecule that will interact with this light and go to the singlet state, that is an excited state, and then go to the triplet state. When it is at this triplet state, it will actually interact with other biomolecules and with the triplet state oxygen, which is the natural form of the oxygen in the body. And then these free radicals and singlet oxygen will generate this cell death. Here we have an example of the cell death happening with the light dosage varying and the time dosage too. We have some images of the applications. Here we have for carcinoma. We see here that it is non-invasive. We have the presence of some scars on previous surgery. But here we don't need to have surgery to do it, just the photosynthesizer and the light. We can use it for an oral neoplasia, for fungus and bacteria too. And one of the interesting things is that we are aiming to apply this to your universal healthcare here in Brazil to treat skin cancer, so directly from our institute. To be a photosensitizer, you need to have good therapeutic action, good fluorescence, and biocompatibility. Here we have some examples of porphyrins that are already in use to PDT, and also some chlorines. And that's why we want to study these kinds of molecules. They have good resonance in their microcycle, which enables to increase the spin-orbital coupling, which increase the intersystem crossing. This is the important thing to consider when trying to find molecules that are good for PDT. The molecules which I'll be talking about here today are these ones. They are tetraphenylporphyrins with Chalcone ligands. And I'll be talking about the methodology used to determine the triplet formation quantum yield of them, and also the intersystem crossing rate, which are one of the rates that can happen. For that, we need to understand which transitions can happen between the fundamental state and the excited state. So most molecules are in the fundamental state, and when they absorb light, they go to this excited state. From there, they can go mainly three transitions, which is fluorescence, a radiative one, non-radiative transitions, which will generate heat, and intersystem crossing from the singlet state to the triplet state. This one is the important one for PDT, and this is the one we will be studying here. From this, we can get the fluorescence lifetime, which is the inverse of all of the sum of the rates that are involved in this process here, and the quantum yields too, which will be mainly focusing of the intersystem crossing. For that, we develop a technique which is called double pulse induced fluorescence, where we use a laser photos to give two pulse lasers spaced temporally in order of nanoseconds that will arrive at the sample at the same range of space. So they will excite the molecule consecutively and will give us the fluorescence resulting to that. And here we will have a graph that represents the behavior the molecule will follow. So we have the population fraction for the time, where the population from the singlet state molecule will follow the fluorescence we observe. So first, the first pulse will excite the molecule, and all of the population present there will be excited to the singlet state. And from there, they will decay. And when the second pulse arrives, some of the molecules won't be present, because when some molecules are actually returning to the fundamental states, others will be going to the triplet state. There, the lifetime is actually longer. So in this scale, it will remain only crescent, the population. So when we have the second pulse, we will have this decrease of molecules that will actually be trapped in the triplet state. With that, we can actually relate the fluorescence we observe with the lifetime of the molecule and also the distance between the two pulses. And with that, obtain the triplet formation quantum yield. We can see this translated here, where we can see the signal of the fluorescence for the time, varying the pulse energy of each pulse, right? So we can clearly see that the second pulse is actually lower than the previous one because of these molecules that are trapped in the triplet state. So separating these two fluorescence, we will have a behavior that will actually be saturating through the increase of the pulse energy. And when we get to be in this saturation, I'm sorry. When we actually get to be in this saturation limit, we get to determine the triplet formation quantum yield. That for these molecules, we're mainly at 30% with exception of the CP3, which is pretty high for the molecules. The molecules that are used for PDT actually, they have lower triplet formation quantum yields and work pretty fine. So this has some good things that can work out for us. With the results we obtain, together with other ones like the fluorescence quantum yield and also the fluorescence lifetime, they translate to the rates of each process. So the radiative, the intersystem crossing, and the non-radiative. We can see here that varying these properties, they can have really good impacts on the rates the molecules have. So for CP3 here, we see that the non-radiative rate were really high compared to the other molecules. And what we discovered from that is that compared to other molecules that are more similar to them, it has a higher electronegativity because of the NO2. He is responsible for deactivating the phenyl ring, which created a new non-radiative decay path. And this is what we did there. So thank you very much for the time here, for everyone present. And if you guys want to meet the group, we have the website where we can check it out. These are the professors responsible. Leonardo De Boni actually is responsible for my research. We also have Cleber Mendonça, Lina Mussoguchi, and we are located in Brazil, in the state of São Paulo, city of São Carlos, in the University of São Paulo. So thank you very much.
Thank you very much, Carolina. It was a very, very interesting presentation. Now I want to know if there are any questions, please. So we're going to wait a minute in case there are. Oh, okay. Yes, we have some question. Are there any other non-invasive techniques? What is the advantage of yours?
So the advantage is we don't need surgery, and it's low cost. I mean, the laser obviously will be high up in cost, but when we actually got to optimize it, it can be low cost. So you don't need surgery, you only need the photosensitizer and the light. And other non-invasive techniques, it will be, I mean, the PTT, that is photothermal therapy, that will be mainly the same thing, but the mechanism to self-death will be through heat. But I don't know of any other kinds of without being surgery.
Okay, thank you very much, Carolina, once again. I think we all found your investigation really interesting. Now we're going to welcome Emilia Pastor. She is archaeoastronomer in the Third Eastbound Museum. Her research primarily focuses on the sky lore of prehistoric Europe and its societal implications across the region. Her research endeavors to unravel the extent and nature of astronomical knowledge and beliefs among prehistoric populations by amalgamating archaeological, ethnographic, and anthropological evidence, possessing dual master's degrees, one in archaeology and another in physics and astronomy from Eötvös Loránd University in Hungary. She furthered her academic journey for completing her PhD at the same institution. Her doctoral thesis delved into the orientation of the ancient tomb of Saint-Edmond in Egypt. As a member of various international professional bodies such as SIC, ISAC, and ISARS, she is also a founding member of the Axis Mundi research group, which specializes in studying late Neolithic circular ditches. Conducting extensive fieldwork across Europe, supported by Chalmers University in Gothenburg, Sweden. She has also participated in multiple expeditions in Inner Asia. Her scholarly contributions extended to over 100 publications in STEAM professional journals and conference proceedings, including Antiquity, European Journal of Archaeology, and Archaeological Balloting. Please, let's welcome Emilia. Wait for me a minute. I'm going to share your slides.
Okay, until I see it, I would like to say thanks for the invitation, because it is a very rare occasion that I can talk about archaeology, my results for non-archaeologists. So it's a special pleasure to me to talk about it, and I hope that the theme or the topic I have chosen, you will also like it. In my young age, I wanted to be an astronaut, but then I realized soon that I am afraid of flying, which is not so beneficial for an astronaut. So I had to change my life career. My second choice was archaeology, as I love stories about ancient cultures and their secret knowledge, and which was difficult to decipher. So these two interests led me to study astronomy and archaeology at the same time, and the sky lore of illiterate societies.
Sorry, Emilia, to interrupt you. I'm sharing your slides now. You can begin.
Okay. Okay, so this led me to study astronomy and archaeology, and the sky lore of prehistoric society who are illiterate became the target of my research. In my presentation, I would like to share the results of my research on the European Bronze Age celestial symbols, which I have been working on for a long time. The Bronze Age, the European Bronze Age, cover the time period of between 3,000 years ago and 4,500 years ago. So it was quite long ago in human thinking, but not so old as the stars are. And this hypothesis I developed supports all diversity of the symbols, their appearance in different regions, even in different continents, and offers new way to study the archaeology and the sky lore of prehistoric society. Next, please. Next. Next slide. Yeah. Among the Bronze Age artifacts, there are ones which are almost exclusively made for bearing a symbol. These are the pendants and the pins. And the Carpathian Basin is really rich in these artifacts. Most of them are assumed to represent the sun, but neither their diversity in structure and nor the widespread, both in geography and in time, were ever questioned. I have compared the structure of these symbols with the basic structure of the atmospheric phenomena, and discovered that there are many common features, many common characters among them. And I think that these symbols are not simple sun or moon symbols, but actually we can call them light symbols. This theme is very rich, so I can share with you only some basic notions. Next one, please. Next, yeah. One of the most frequent type is the concentric circles, which can depict the solar halo or lunar halo, 20 degrees halos, or coronae. Next one, please. Next. Many of the European Bronze Age gold treasures, not many, but the majority of them is covered with these motifs. Next, please. In the Carpathian Basin, you can see these red circles on the map. That's the Carpathian Basin in Europe. And in the Carpathian Basin, almost any type of artifacts, archaeological finds, are decorated with these symbols. Next, please. One of the strangest symbols is, or the artifacts are these special Danish belt plates, which are considered to be sun symbols, but nobody ever tried to explain why there is a spike in the very middle of them. I think that they also represent atmospheric phenomena, the sun column, and there are many smaller such pendants in Central Europe. So you can find it almost every archaeological place. Next, please. Beside the concentric circles, the light cross, or the so-called wheel cross symbols, is the other most frequent one. Next one, please. These symbols, these cross and light symbols or motifs, are made the greatest impact on the prehistoric people, as they frequently ornamented many types of unique objects. Starting from the Middle Bronze Age, there were hardly any archaeological culture in Europe which didn't use them. Next, please. This cross and wheel cross symbol is very popular in the Carpathian Basin during the Bronze Age. You can find it many or almost any type of artifacts. I was very lucky to excavate a Bronze Age cemetery with a unique female graves whose jewels also represented light symbols. One of them was a beautiful amber pendant with a cross drilling, and the others were a necklace with such a circular disc with the spike symbols, the sun column symbols. Next one, please. Not only the sun column and the wheel cross symbol, but also the sundogs can be seen on the artifacts, archaeological artifacts, with the three suns, representing the three suns on these jewels. Next one, please. There are special and beautiful arm rings with crescent-like endings, which I think that they represent not the lunar dogs, not the sun dogs, but the lunar dogs, the moon dogs. Next one, please. This special halo with parhelia could have inspired the so-called sun, bird, and sheep symbols. Next, please. Which is a very typical motif of the late Bronze Age ceremonial drinking vessels called situlas. And these beautiful vessels were manufactured in the Carpathian Basin, and all of them are decorated or ornamented with this symbol. Next one, please. Sometimes the sun, the circular form of the sun in the middle of a halo became distorted and take the form of a rhomb. And we can also find this rhombic depiction on the archaeological finds from the early Bronze Age, which are more than 4,000 years on the upper part of the slide, but also we can see them on the center of the Sami shaman's drums. And there is a very special one which was found near Stonehenge in male graves, which decorated his breast, and it is also, I think it is also the representation of the sun. This is the so-called bush barrow lozenge. Next one, please. It's very rare, or sometimes you can see a complex halo in the sky, and you can also find them among the archaeological finds. However, they not exactly depict the sky phenomenon because the artist had to work from memories, even if they had seen these phenomena in the sky. I also believe that the famous winged sun from Mesopotamia and ancient Mesopotamia might have also depicted such phenomenon. Next one, please. The identification of these light symbols could open different new trends in the archaeological research. I can show two of these case studies. One is a special role, their special role in burial customs. When in the Bronze Age, it was a custom to cover the urn with a bowl, and the bottom of the bowl is very often ornamented with such symbols. We know from the ethnographic records that people like to carve or paint sun or moon symbols on the coffins because they believe that these symbols can offer light for the deceased on their long way to the netherworld. Maybe this is the same, we can say the same interpretation for this Bronze Age burial custom. The second one is that these symbols, these celestial symbols, has a very strong connection with the symbol of the power, with the power. I think they absolutely express the symbol of the power, because in the European Bronze Age, the most precious object made of gold or nice bronze, they always decorated with some of these symbols. So it shows that it proved that they have a strong connection. There was a strong connection with this special, not a simple sun symbol, but with these special light symbols and the power and the celestial realms. Next one, please. You might heard about the famous, world famous nebula sky disk. It also represents some atmospheric phenomena as well, beside the sun and the moon. And also maybe these small dots, the group of these dots might represent the Pleiades, but they also shows the rainbow on the upper right part of the disk, and we can also see two other arcs, golden arcs, which is one of them is missing, and they might have represented such air phenomenon when you can see on the horizon before the sunrise.
Are there any other non-invasive techniques?
Sorry? And you can see it after the sunset on the horizon as well. Next, please. Next. We are very lucky because these very complex, I can say that cosmological objects we are lucky in the Carpathian Basin because we also have a special object like the nebula sky disk, but we also know the function of this object because it was an armlet, and on the surface of this golden armlet, which is quite a big one, so it might have been worn in ceremonial events, you can see almost every element of the sky, the daily sky and the night sky on this golden object. Next one, please. I can't help showing these slides to you because you might know it. These are almost contemporary, beautiful ceremonial objects, but they are extremely similar to the Bronze Age ceremonial object as well. So it is surprising to see that still they are used in our age as well. And I don't know how many time or how much time I still have, but if
yes, I was going to say you have 1 minute.
1 minute. So the next one is a short video, a bit more than 1 minute, so you can stop it when you want. And it was made in the Carpathian Basin among the mountain, and when we could see these wheel cross motifs, which must have made the greatest influence on the prehistoric people as well in the Carpathian Basin. Thank you for the attention.
Thank you very much for your presentation, Emilia. It is a really interesting approach of astronomy and archaeology. I'm going to give some space for questions. I think, let me see. I think we have one question, and the question is: do you know some optical techniques to get more information about the archaeological object?
Atmospheric. I mentioned the rainbow. It's quite rare, but still the nebula sky disk prove it. And I think the northern light might have been also presented, and it's strange that there are some special or unique weapons which are richly decorated, such symbols which look like the storm clouds. There are no lightning representation in the Carpathian Basin, but this strong, this stood for the storm goddess or something, some spirits, storm spirits, because it has a great influence.
Okay, thank you very much for your answer. As I said, it is a very interesting and I think innovative approach of making investigation. Thank you very much for your present. Now we have Dr. Carmina Londoño. She is member of the Senior Executive Service of the Federal Government of the United States. She is member of many other institutions and organizations. She's going to tell us now about her career and about women in optics. We welcome you, Carmiña. Please continue.
Buenos dias. And yes, I'm going to speak in English. It's just that, okay, let me get this set up. So I'm going to deviate a little bit from what other folks have done because in the last few years, I've been more in management of people that are supporting scientific research. So I don't have any particular research that I can tell you that I've done lately. I'm going to give you a little background about what I've done. And I was told to also take the opportunity to perhaps give some advice, since most of you are younger and you're at the beginning of your careers, which is very exciting. So I'll start by saying thank you so much for inviting me to this event. This is an excellent opportunity. And just listening to all of you with all of this exciting work that you're doing, it makes me wish, geez, I wish I could be alive another 100 years, because there are so many discoveries and good things that we can all accomplish through science to make our world a better place. Anyway, on that note, so I'll just tell you, so I was born in Colombia, south, next to Ecuador, and I came to the US when I was rather young. So my education was from the US. So I got a bachelor's in physics, then I got a master's in optics, and it was optical design. I don't know how many of you consider yourselves optical design engineers, but basically I figure that a lot of the work you all do in astronomy, in medical science, in archaeology requires a lot of optical instrumentation that allows you to do those measurements. So I was at the end doing the optical engineering, the actual design of the optical systems. And then I worked for a few years in industry, and then I went back to getting my PhD, and I'll tell you a little bit more about that. Okay, so I started my career after getting my master's by working at a research laboratory, which doesn't exist anymore. And we were doing characterization of xenon fluoride lasers. At that time, there was a lot of interest in creating, under the Strategic Defense Initiative, these lasers that could communicate with satellites. And so so I was the lens designer that actually designed the optical system. And you can just see by this that it takes a team. And I think you all really know this. You got to work with mechanical engineers, with physicists, with chemists. There was a whole, and I was rather young at that time. And so that's something a theme that I wanted to emphasize as I went through my career, just how important it is to have that ability to work well with people with different disciplines. Because if you may know a lot about your particular area, but it's necessary to be able to communicate with everyone else. So we did a proof of concept with this instrument, and then we actually then scaled it up to a large laser. And when I say large, is the primary of this particular laser was 3 meters in diameter. So we're talking a big, gigantic laser. And in fact, because and I still am a small woman, I actually had to crawl through these tubes in order to do the alignment. Because all the other people, the technicians, were much bigger and they were afraid of claustrophobic. I don't know. Anyway, so it was a very exciting month and about a year and a half that we dedicated to this particular project. And on this side, this is a thing that I would say to many of you younger folks, that as you go through your career and you are advancing your knowledge in the sciences and engineering, also keep in mind or make a list, what are these skills that you're learning? Because like, for example, here, obviously, it was primarily the science, but I had to learn a lot about large instrumentation. I had to learn how to deal with vendors. I mean, because I had to go inspect the big optics that someone else was making. We had to apply for monies. So, and you have to write technical papers, and then again, teamwork. You can see that at the bottom. I have it at the beginning and I have it at the end because it's really important as you move along in your careers. Then I moved, so I was with a research lab, then I moved to the Polaroid Corporation. Doesn't exist anymore. It seems like I've worked in places that after they hire me, they go bankrupt. Anyhow, the Polaroid doesn't exist anymore, but at the time it was a very exciting company to be working for, because at the optical engineering department, we were doing a lot of modeling for medical applications, for large manufacturing, large quantity manufacturing. I was able to get patents out of that work that we were doing. This, for example, is a barcode reader for when you go to the supermarket. So we were actually, this is, a good 40 years ago, doing some of this primary work. We worked with Mitsubishi to do the optical designs of these CD players that now they're so, actually you guys don't even use CDs anymore. You now do MP3s and all these other things. But at any rate, we did a lot of medical imaging. We worked a lot with a company that was addressing macular degeneration in the eyes and how to create a headset that would allow people to do face recognition. So it was a whole variety of work that I was exposed to. Now, at this stage, it turns out that I kind of concluded that I had a master's at this point in my career. And I could see that if I wanted to advance further, I needed to get a PhD. So lucky for me, and the stars lined up. There was a university, Tufts, that was starting a PhD program that I could join and work on it part-time. And so I continued to work at Polaroid, but I was able to then do a particular thesis, take more courses, and it took 7 more years after my master's to get my PhD. And I did it while I was working. And I don't recommend it. I think it's better if you could go to school full time, but if you can't, you got to do whatever it takes. So at any rate, I worked on, so a lot of the bread and butter Polaroid at that time was injection molded plastic elements, and plastic lenses are very susceptible to temperature changes. So what we did is develop a whole mathematical modeling and then actually built it of what we call kinoforms, which are these diffractive elements. So essentially, it's a grating. It's actually cut into the lens, and it has an aspheric polynomial distribution that you can then use. You use the other elements to correct for the optical aberrations in your system, but then you use the kinoform so that when the lens expands due to temperature gradients, you actually now correct the defocus element, the defocus that it results in your system. It was actually quite a clever idea. And it wasn't all mine. My professor suggested it, so I had to work into it. But anyway, I got to do the work and I got the PhD, so that was good. So I wanted to also take a quick deviation here to tell you all younger folks. I think it's very important, especially, like this OPTICA chapter. I think that it's very important to be involved in professional society events or leading them, because it helps you develop skills that you may not necessarily be getting at your work. You may not be the boss at your work, but in your chapter, you may have a leadership position, and that gives you those skills that you're going to need as you go forward in your career, and it also allows you to network, to get to know more people. So this is just, at that time, I was very involved. I was a board member of YES. I was primarily working with the YES-PIE, but you got to get involved in chairing committees and in just in a lot of different things so that you're able to network and also develop skills. Anyway, and then of course you don't sleep much, but then at that time you're building your career, right? So then I quickly, just to mention my personal life, unfortunately, took a crumble. I got divorced, anyway, a few other things. So I took it. So the point of this part of the story is that you got to remain flexible. You got a lot of ideas. You got you think your life is going to go one way, and then life throws you some other stuff, and you go, oops. So you got to like get up and say, okay, what do I do now? So anyway, it turns out that without going into a sob story here, I wanted to get out of the Massachusetts area because just bad things were happening there personally. So I applied to the American Institute of Physics, and I applied to several institutions, and I was able to get this fellowship to work for 1 year in the US Congress. And so it was a total different thing. I was actually there working in the Committee of Science with George Brown, this guy here, he died already. And I was putting on hearings, and I was learning about the US budgetary process. I mean, I was actually working in Congress. I mean, obviously my role was tiny, you know, I mean, we were supporting the Congress people, the elected officials. It was a very exciting year. You get to see so much how actually the US funds science. So it was a very exciting year, and it put a different perspective on my life. And then I went into the government. I had started in industry. I thought I always would work in industry, and I ended up now joining a federal government agency, which was the National Institute of Standards and Technology. And I was there for 13 years, and we did lots of work. I got to travel to many places, attending many standards committees, doing laboratory accreditation. Anyway, if we had a lot more time, I could tell you about all the different things. And I went into management. So that was my first foray into management. So then I joined the National Science Foundation, where I spent my last 15 years. And the National Science Foundation, I looked it up. They are the counterpart in Ecuador to, I have it here, CENESIT, the Secretaría de Educación Superior, Ciencia, Tecnología, Innovación. So then that's just to give you the context of, so the NSF quickly just covers all the areas of science and engineering, very similar to the CENESIT. And it has, the budget is about $10 billion. Now remember that in the US, the billions are 10 to the 9th, and in the Latin system of the rest of the world, because the US is always trying to do things differently, it's 10 to the 12th. Anyway, so you can put it in perspective. But very similar to your institution, we get proposals, we set up panels that evaluate the research merits, and then we either award them or we decline them, and we work very closely with the universities, and it invests a lot of money in STEM education. So at NSF, I'm almost done. I'm looking at Anna because I'm trying to figure out if I got a few minutes. I started in the Office of International Science and Engineering because I've always been very committed to international cooperation. Then I worked in the Division of Materials Research. And so, and then I ended up working as a program director in the Engineering Research Centers. And this was a big challenge. So I was assigned 5 different centers, primarily, as you can see, in photovoltaics, the power grid, biogeotechnics. Now imagine that, you know, I come from optics. What am I doing with biogeotechnics? That's another thing that as you move along in your career, you know, you can choose to become very, very focused on the area you know, and that's good. Or if opportunities present, you broaden and you take your scientific and engineering and all the skills you built, bang, and you take on the next challenge. So these are centers, engineering centers. They're for about $50 million for 10 years, and you are shepherding, you are leading those centers. You are the one that gives them the money. You're the one that evaluates them on a yearly basis. You don't do it alone. You have a team of experts that go. Anyway, it's a very challenging, it's a very competitive program, and it's a lot of responsibility to manage these centers. And then after that, I went back into management.
Arminia,
So
sorry to interrupt
so
you.
let me,
I have a minute.
just about done. Thank you, Anna. So then I went back into management, and just to tell you again, with the optics background, you know, it served as a basis for being able to get involved in all of these different areas. We did electronic photonics, we did energy, we did communications and circuits, and I was the deputy director. And anyway, it doesn't, you know. So let's finish up, because this is my last, well, I have one more slide after this. So essentially, I want to deliver the message to all of you. I think a career in optics, it's a tremendous opportunity. It opens a lot of fields. It could be astronomy, it could be archaeology, it could be medical applications. I encourage you to continue. It doesn't matter that I started as a basic lens designer. You know, by the end of my career, I touched a lot of these subjects. And the big thing is our science does make a big positive societal impact. And we are making a difference in advancing equity and inclusion. And what does the future hold? So many things. So, you know, okay, so last but not least, I know a little bit about this Ecuadorian writer, and I really like what she says here. So I'm going to read it in Spanish. I hope you don't mind, but I just really like her approach. She says, escribo porque soy cazadora de sueños, porque llevo a la esperanza de sombrero, porque me enamoro de la vida cada día, porque me empeño en no ver el lodo en un charco de agua, sino el reflejo del cielo. Es decir, el reflejo de la óptica. Thank you. Thank you so much. This is a great opportunity, and I hope that I can continue to be supportive of all your efforts. And I wish each of you, which I can't see, much success in your careers. May you conquer the stars and are able to come back and give us a lot of wisdom. Thank you.
Thank you very much for your intervention, Carmiña. It's been really inspirational. You are a very impressive woman, and I'm sure we all have learned a lot and have many insights about how the future looks for us. I think there are very young girls here, as I said, in different stages of their careers, and listening to you, it's been amazing. Thank you very much. I think there is a question. Okay. First, we have. There are two questions. Okay.
Anna, I can read it. I can see it. And one about. So I actually don't think it is a good idea to have programs, and I think many countries are starting to do that, where they pay for you, and then you do have to go back and do service. I think it's a good idea. I personally didn't. It's a much longer story how we ended up in the U.S. So, but I did. I'll tell you very quickly. I did for several years. When my life was falling apart, I really wanted to go back again to Colombia and just be part of and at the time I looked for opportunities and it was very limited. And then my dad actually said to me, why don't you stay there? Why don't you try to help as much as possible from where you are? If you come here, you're not going to be able to do much. So at any rate, that was the path I took. But I do agree that it is good to pay back. It's very good to pay back because we have a lot to offer. Second question, I hope that answers your question to Adrian. And the second question was for undergraduates, would you give to undergraduate students so that their academic activities are those for the best? I think there is no magic formula. I think you remain open. You listen to your professors. You talk to other people. You go to conferences, if at all possible, or virtually, and you try to figure out what part can I bring to this project, and what are the opportunities. And it's just flexibility and curiosity. You take what you're learning, and you remain true to that curiosity and that inner part of you that says, I do want to make a positive impact. I'm sorry, I'm not sure that I have a better answer than that. And thank you for asking.
Okay, Thank you very much for your presence, as I've said. Now I'm going to introduce our final speaker, closing this interesting and enriching cycle of talks. We have Dr. Carla Herman, Assistant Professor at the Faculty of Physical and Mathematical Sciences of the University of Chile. She is a prominent Chilean physicist specialized in quantum optics, both experimental and theoretical. She plays academic and research roles at the University of Chile and the Millennium Institute for Research in Optics, MIRO. In 2017, she is a recipient of the L'Oreal for Women in Science Chile Award. Carla did her PhD in Paris in the group of the 2012 Nobel laureate in physics, Serge Harochi, under the direction of Professor Jean-Michel Raymond, and continued her postdoctoral studies at the Joint Quantum Institute in NIST in USA with Professor Paul Lett. She leads several scientific projects and participates in several science outreach projects, leading the radio show Let's Get Physical on TXS Plus, and also making content on her Instagram. I recommend you to follow her, @quantumcarla. In 2023, she was recognized by Forbes Chile magazine among the 30 most powerful women in Chile. We welcome you. Carla, please continue.
Hi, everyone. Thank you very much. Do you hear? It's okay, the volume?
Yes, we can hear you fine.
Okay, great. Well, thank you very much for this invitation. It's an honor for me to be here and also to hear all the histories of the other women presenting here today. So thank you so much to share all that you have been able to experience during this career. Today, I was asked to talk about what we do here in Chile. So I will talk about quantum optics at the University of Chile, because this is where I work. So just to give you a bit of context of my career, I studied the undergrad in Chile in the University of Concepcion. And then immediately I started a PhD here in Chile also under the supervision of Carlos Saavedra Rubilar. And then not at the middle, but like 1 year after, I got the opportunity to start another PhD in France in experimental physics with Rydberg atoms, with Jean-Michel and Serge Haroch. And of course, it was an amazing opportunity, so I left. But since I had one scholarship from here in Chile for my PhD, I was a bit forced to stop that scholarship, but still to finish the first PhD. So at the end, I had to do 2 PhD, which I don't recommend because I was working 15 hours per day, Monday to Monday, nonstop. It was really hard, but it was the only solution to not pay back the money. And I took it, so that's it. It was an incredible experience, of course, to be in France, and I was coming to Chile to work by person during the holidays and stuff like that. Then I went to the US, to the Joint Quantum Institute and NIST, to do a postdoc with Paul Lett in the squeeze light generation. And then at some point, I came back in 2017, and I did a little postdoc here in photonic crystals, and I was soon hired as an assistant professor at the University of Chile. And a few years later, I became an associative researcher at the Millennium Institute for Research in Optics here in Chile. So this is a little bit of my how did I get here, where I am today, and also to give a little bit of context on the map. So this is Chile, very long, at the end of the world. I work here in Santiago. This is the capital. So this is the Faculty of Physics and Mathematics. And here in this building, in the old building, in the -1 floor, we have the lab and the Department of Physics. And I collaborate a lot with another professor that I want to show, because this is the specific topic that I will talk in this presentation. And his is like 500 kilometers to the south. And he's working in this beautiful university, which is wide open, and all the campus are in one big campus, and it's very, very beautiful. So the University of Concepcion. And this is the team working with us in the topic that I will present today. But actually the team is quite big right now. We have plenty of people, our collaborations working in different topics that I will also tell you now in the next slide. So these are some professors, students, postdocs, and different position in the career. So what do we do here in my group? We have a quantum optics group, and we study what we call quantum state engineering, which means that we want to create quantum states at will. This is more or less what we want to do. And we focus in 3 different research lines within this big one, which is the generation of no Gaussian states, the generation of a squeeze light, that is very important to what the first speaker talked about, the measurements of gravitational waves. This became very important there. And also the propagation of quantum light in linear arrays like photonic crystals and things like that. So this is more or less what do we do here in my group. And this is the picture of the lab. So this is more or less how does it look like. We started in 2019 or 18, we got the first optical table. And as you might know, the fundings here in Latin America are very poor in comparison to the US or Europe. So the first year was just to buy the optical table. The second year was to buy the laser. And then the third year was the pandemic. So after these 2 years, we started to really make experimental physics here. And so this is how does it look like, the squeeze light generation. So something like that. And we also, as I said, we study how light is propagated in this kind of arrays, which are photonic crystals. So we study what happens if you propagate a quantum light in a dimer or in a trimer. And we have seen in some papers that you can create you can start with factorized states and then get entanglement of these states. So this is a very beautiful work that we did in 2019. And then we have now generalized this work to N waveguides. So we found like analytic solution for this system, and we can see that we can create entanglement in N different waveguide system. So it's submitted now, and you can find it in arXiv if you want to look more. And we also study how you can propagate, how you can protect quantum light, which you know is very fragile, especially when it comes to losses and the coherence process. So we study this kind of systems that are photonic arrays, but with some topological characteristics. So you can protect not only the intensity of the light, but also the intrinsic characteristics of the quantum light. So it is very interesting, and we have been doing here very beautiful things. I don't have time to explain everything. So as I said, here in the group, we work towards the macroscopic quantum light generation. And I like a lot this topic because somehow when you study physics, quantum physics, you are normally told that the quantumness appears just in the single photon regime, or when you have little light, like little intensity. And we have proven that this is not true, and you can actually have this macroscopic light with quantum features, and that can be observed. So this what we have done in 2 different works in 2023 and 2020 is that we have seen how a classical state, which is this coherent state that is always people teaching in the universities always refer to the coherent state as a classical state, and for me this is a mistake. And how this classical light can evolve into this very highly quantum states, and also here, but with some other different configurations, like this spiral and this kind of Schrodinger cat, but with multiple earrings. So this is what we do, and this is important, as I said, because when you learn quantum optics like 101 at the university, you always learn that the coherent state is a classical field. And the only quantumness that appears is here in this uncertainty area, you see? But if you have like very intense light, like a coherent state, but very intense, this small area doesn't depend on how intense is the field. So when you have a very large like vector here in this space, at the end, you don't care about this tiny little bit of area with this uncertainty. So you refer to it like a classical state. But actually it's not exactly like this. You can exploit this quantumness and create very big quantum states. This is what we have proven in these works. And so normally you can characterize quantum state by two ways. One is to look into correlation functions, which means detection of coincidence. And you see that when light is below 1 in this coincidence measurement, you refer to this light as a quantum light. But this is because it's related to the statistics of the photons. And if it's coherent of thermal, you will see a 1 or something above. But this is not the only way. You can also characterize this negativity of the Wigner function, and you can also see very beautiful shapes in the phase space that sometimes is not directly to see in the statistics. This is what we have claimed in our work. So I'm running out of time because I put my the timing here, but this is more or less what we do. So we start with a classical field, and we see how in the phase space this starts to evolve to this beautiful, for me this is quantum art made by nature, and you can start to see this like a mandalas thing, right? Which are like kind of, in this case, are like Schrodinger cats with many earrings. And every time that you see this pattern about maximum and minimum in the phase space, you know that this is useful for quantum metrology, which means how to measure with more precision using quantum resources, whatever you want to measure, as for example, the gravitational waves detections. So this is some things that what we do. And there is another paper, the other one that I showed you in the beginning, which is very similar. This is just a normal James C. Cumming model that everyone sees, and we see something very beautiful also. So we see how this classical light starts to spread. At the beginning, you have a normal Schrodinger cat, and then you have this focus states generation, which are very interesting for quantum information, for metrology, for many things, and they are very, very, very hard to achieve with high photon number. So what we did in this paper is that we proved that you can transform this classical light to this highly quantum light with very, very high fidelity with respect to a target state, like a normal target state. And this is why if some people that might have taken here in the audience the quantum optics course, you always see this picture, which is the Rabi oscillation picture. So the Schrodinger cat is created in this region, and then what we have seen here, this focus state, are created in this next collapse of the wave function. So this is very, very beautiful. And what we are doing now, we are trying to characterize this macroscopic quantum light, because since it has plenty of photons, you cannot just do single photon detectors. You need to go to another kind of techniques to really understand that the state that you are creating in the lab is actually a quantum one. Like try to claim that your theoretical results are true. So we are trying to use different here correlation functions that I don't have time to explain. I'm sorry, because I'm running out of time. But yes, so this is we can try to measure entanglement or some correlation functions that are like between the field and the intensity, to claim that what we are observing in the lab is indeed quantum. So this is some things that we are doing right now. So with this, I am ending the presentation. This is a very beautiful scheme that I normally, when people ask me to do some outreach talks, I start with this big picture that is very important when you do science to dare to think different things, or at least to question where the theory applies and where you still have a room to improve or to push the horizon of knowledge further. and how the quantumness is very exciting, and how here in Chile, and I think in Latin America, we have the potential to join this effort for quantum technologies and advancing in quantum technologies for different research or technological applications. So thank you very much.
Thank you very much, Carla, for your presentation. I think I speak for everyone in our lab. We are huge fans of your divulgation work. And now hearing about more about your investigation work, it has been great, really great for us. Now I'm going to
I can read the question also.
Yeah, could you please?
So thank you. I had more prepared, but I realized at the middle that just 12 minutes was not enough, so I went a bit faster in what I wanted to explain. So about your question, how quantum entanglement and quantum superposition enhance measurements capabilities in quantum metrology? Actually, it doesn't. You can have an state, just like a field state, without any entanglement. It might be created because of the entanglement, for example, with atoms or whatever the medium you have. But once you have your state, it can be disentangled to whatever and still have quantum features, especially if you see them in this phase space representation, which is the Wigner function. So for quantum metrology, you just need that. You don't need an entanglement, necessarily, but you need to have this structure in the phase space, which is very rich to resolve different parameters of measurements that you want to do. In some other experiments of quantum metrology, what you do is that you send like entangled beams, and then you know the correlation, the quantum correlation between these two guys, but one of those beams are like going through some materials or whatever characteristics or parameters that you want to measure. And then you recombine again, and by like an interferometer, and then by looking the correlation signal that has changed because one of the beams entered this medium, then you can extract with more precision the parameters or whatever you are studying in this medium. So we have these two ways. But for example, for the gravitational wave detectors, they didn't do that. They just put directly squeezed light without entanglement, and they can improve the precision measurements in the interferometer.
Thank you very much for answering his question. Now I'm going to give you a very little introduction. As we all know, we are going to close the event with a conversation about gender issues in STEAM, right? So I would like to give you a little introduction in related. Sorry, I'm going to share my screen. Okay, now I'm going to give you a very fast presentation about challenges related to gender equality in academic work and social environments. And then we can all discuss a little more about it. So first, I have here some statistics that where we can see that women have made tremendous strides in education and now account of 44% of college-educated workers in STEM occupation. However, when we analyze their underlying data, we can see divergent patterns of gender inequality. Men continue to represent the vast majority in degrees in STEM fields such as geosciences, engineering, economics, mathematics, computer science, and physical sciences, while women are overrepresented in life sciences, psychology, and social sciences. These gender disparities appear to be increasing slightly over time at the undergraduate level, with possible implication for gender differences in employment, salaries, academia, and beyond. In this slide, we can see how the representation of women in physical sciences overall is one of the highest within the core STEAM subjects, and it's growing at a very low rate, but it is growing. But equal representation is still many, many years away, given the current rate of change. Here we can see why. Because even though women are now a large part of the college-educated people, we can see that in the workforce, we are not very well represented. In 2022, that is the last actualization in these statistics, we can see that women are barely 26% of the work labor force in STEAM fields. And we can see why, because women are often discouraged to pursue their careers with a variety of for a variety of reasons, but we know that there are harassment issues, there are inequality in payment roles, and many others that I hope you will give me insight later. The most important that has been discovered and is being awarded with the Nobel Prize this year in economics is the gender gap in the pay gender gap in the labor market. Even though women make up 52% of the workforce in the United States, with at least a college degree, these statistics are from 2019. We have a very very hard underrepresentation issue. We can see here a 2000 year gap where women stopped working around 1910, and we started working again, at least officially, when the contraceptive pill was invented, because we had more facilities it was more easy for us to decide when to become mothers, even though we are still underrepresented in the workforce. The principal issue we have seen, the investigators have seen here, are what they call the maternity effect, where a woman, when she became mother, has a very deep issue with their pay. Even though many countries have legislation for it, and women tend to be more educated than men. This is my little presentation, and I would like to hear your insights, the speaker's insights, or anyone who wants to say anything about the issue. Thank you very much.
I can start if you want.
Thank you.
For me, this is a very important issue, because I think, and I think that it might not be the same going on in like the US or Europe, but here in at least in Latin America, it's not, how to say this, it's not, we cannot reach still this co-responsibility in families. So indeed, for us, I am also a mom of 2 little boys. And so indeed, for us, it's a bit more difficult to stay like in shape in the academics, because we have to take other responsibilities, which are normal. I mean, I decide, and I guess the people with children decide also to become a parent. but still you have the impression that you never reach the same levels as your colleagues. And then the problem arises because you are tired with some obligations. And if you want to advance in this career to get, for instance, a promotion or some leadership position, blah, 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 you are asked to fulfill several items, which for you will be way slower to achieve because of your situation, which is it's chosen, but it still is hard. And I think that this is when it comes to maternity issue, is one of the main difficulties, because at the end, I think that you will always choose to be more with your family than in your career, and this immediately puts you like a bias or like a crystal roof to get to higher positions. I think this is one of the issues here, the no co-responsibility that we still have.
May I make a comment?
Yes, please continue.
I was just going to say that even though in general we might think that the US, it's a lot more advanced in this area, and in some ways it is a little bit, but that reality which you spoke about, Carla, it's very much still present in the US. When I was with the NSF, we had several programs, like the advanced programs, because in general, men, and please, any of the young men in here, don't take this as a personal criticism of you, but a lot of the men of the older generation still don't share equally. And women that are in academic positions are often, because there are only few of them in an engineering or physics department, they're put in a lot of different committees. They are asked to do a lot of outreach. They're asked to work on PhD defenses of students. And they feel they have to do all of this to prove that they can also get tenure, that they're also equal, and it's still very difficult, even in the US, even in, so I think that in time, hopefully, especially with the younger men attending this conference, you will appreciate that in order to really advance science and engineering, we need to have the brain power of all of humanity. So I think in time it will make a difference, but right now it's still difficult. And I think it's also difficult for young men who decide, okay, I'm going to stay home taking care of the children so that my wife can go work. Society, at least in the US, still looks down at some of these men. Why aren't you men enough? Why aren't you there working and providing for your family? So I think it's difficult and complex either way. Anyway, just some observation. Thank you.
I agree.
I would like to speak, if that's okay. So I come from like a really interesting example, because my brother, who is younger, is also a physicist. I study physics, and somehow it took for me longer than for him to finish the career. And the support in our family was like as if you ask for me, I don't know, it could be because I was the first studying physics or whatever, but I felt he had more support in the whole context. And it's interesting because now we are both physicists. He is working in the university. I'm doing my PhD here. And giving the example, I think is really important for people to understand that there's a different kind of thinking. You don't need to follow that schemes that society imposed to you. For instance, in the pandemic, what happened was that we needed to like the task in the houses, we needed to divide them. For instance, my brother took care for us in, I don't know, preparing the food and all of that tasks that are for women, but he showed this example. So I think that is like a really important thing to show society with the critical thinking we are learning every day in our careers, that we can inspire not to be in this box. Also, another interesting I don't know, perspective I wanted to share with you was that during my undergrad, I was part of this project that basically we teach people from rural areas physics and astronomy and mathematics. And they were like kind of young, between 12 and 16 years old. And in the last one we did in 2022, it was really impressive to me because most of the attendees were women. And they were so young and they were like, yeah, I want to be an astronomer, for instance. And I was like shocked. But then passing that first emotion, I was understanding that because they are from a rural area, it was so hard for them to move to the capital, Quito, in Ecuador, to study physics, and there was no funding or support from them. And I was like so shocked, because you can inspire people, but you have a lot of problems in society to solve. And yeah, I think there are a lot of things to do, and yeah, we can still discussing, because that shocked me a lot, and I don't have an answer to how to solve that issue in particular.
Can I talk? I'm sorry. So I guess we as women, we face a lot of problems since very early in our age and still very far in our career. Every step of the way we will encounter trouble. We think we need to have a performance higher than all of the men to be noted, to be taken in consideration, because otherwise, I mean, what we are doing here, what we are aiming for, because we can have the same performances as any other man, and they still look down on us, and it's still won't taking us far away. I mean, even in college, we see this in classes where you can have the same class performance as a man, and you still have few lower grades than him, because that's just how the world works today. And this is something that we can't take for granted. I mean, we need to form community, and these sort of events are really important to inspire other women to pursue this kind of things. And since very young ages, like these girls from the rural areas that want to pursue the field of physics. And even when we are far away in our career, we need to continue to have this community, to continue to fund these girls that are low, they're from lower ages, to continue to do that, because we are very disencouraged all along the way. So this is really nice.
Anna, just one last comment. I think everything that everyone has said it's very true. I personally, now that I'm at the other end of whatever the years, I still think that a career in science and engineering, or in optics and photonics in particular, it's really a great choice, whether you are a young woman or whether you're a young man. And it is difficult in many different ways. But when I think about my colleagues or friends that I've had that went into law or medicine, I mean, or teaching at the lower grade levels, those women have it so much harder. I mean, I'm not saying that we don't have challenges, but it's so exciting, the stuff that we're doing. And it is difficult, but I would still encourage young people, look into science and engineering. And I don't have anything against lawyers or against other careers. It's just that I think this career, it's exciting and it offers a lot of rewards. And anyway, that's my parting message. Even though it is hard, many of the things that we have to face to move forward. Thank you.
So, and also to add that I totally agree on that, because even if it's super hard and you have these feelings that you cannot achieve the same level as your colleagues and male colleagues, it is very, I mean, at least in my university, it's very convenient because no one, at least here, no one cares if you arrive at 9 or you leave at 6. If you have to take your children to the hospital or the doctor, you don't even need to ask for permission. You just say to your group, okay, I will be late today, and that's it. And of course, in the same way, if you work during the nights or holidays, no one cares either. But in that sense, it's very flexible. You don't have a schedule. I would say most of the academics positions, you don't have a real schedule. Like besides your classes, of course, if you are teaching, you need to be in the teaching hours, of course. But besides that, it is very flexible, and I think that this is good and it's very compatible with the family life. I will add that.
Thank you very much for all your insights. They've been very important contributions to our talks. I don't know if Emilia, would you like to say something?
Well, unfortunately, I cannot say better. Cannot talk about better things in Hungary either, because there is a difference between women and the career of women and men. And unfortunately, the education now is going to be down, not up, as it would be better. But still, I think that it's very important to to set a good example for the young girls, that they can reach what they want if they have a purpose or object, if they have a purpose for the life. So, and we have in that way, we are in a good situation that still are the member of the European Union. So it means that our girls and boys can go out in other countries to universities and to study. So it helps a lot. But unfortunately, generally, these young scientists don't return to Hungary because they have better place where they studied. But we are optimistic, so we hope that the future will change better. But unfortunately, there is a strong difference between the men and women careers in Hungary as well.
Thank you very much. We have one question on the chat. It says, from your perspective, what role do female role models play in inspiring and supporting girls? I don't know if either of you, of our speakers, are willing to take that. Continue, please.
I can say something. I think it's very important, as usual. Like if you have a female president or a female director of a huge multinational enterprise, of course you have the feeling that you can reach that too. Or if you have some astronauts, female astronauts and stuff like that. So I think that the roles model are very important, but they need to be real, because otherwise you enter another problem. Like if you just highlight the success of the people, they believe then that when they face some challenges, then this is not normal. Then this is me, because whatever person they're up there already, you just know about the success and know how they got there. So I think it's important to show, like to highlight a woman in science, especially the ones that are already like in upper positions, are already got academic position or whatever, but it has to be real, because otherwise it's the same problem at the end, that you cannot reach that, or you are failing in I don't know what. So for me, for instance, it's important when I am invited to this kind of panels to talk about that too. So this has not been just succeed. I have had some very awful breakdowns in mental health, emotional health. There are plenty of times where I have feel, okay, I don't know why I am here, but probably there is someone better than me. And this happens all the time, daily basis, that I have to teach my thoughts to stop. So this is not real. This is whatever you have learned, or trauma, so to say. And for me, then it's very important to address in my role model, to address, for instance, mental health and emotional health. Because it is a bit related to the last question, to the last topic that we were talking about, that also you feel less in comparison to a male researcher, but it's because the system forced you to do whatever they need in this rubric, this evaluation rubric. And most of them, it's related to how many papers, quality of the papers, age factor, whatever. But this is not true. This is not the only way of being a good scientist. So for me, for instance, in my team, I have decided from the very beginning that I will take care of the mental and emotional health of my team. But this means, of course, that we won't publish like crazy, and we will advance way slower than my team, the other professor in the next door. But it's fine. I mean, I already came to accept this situation. This is fine. This is another way of doing science, not to put my family away, and not to force the people working with me to put their families away. And I am good with that way of doing our thinking. So in these role models, I think it's important to highlight that, because if you just highlight the impressive CV that you have, at the end is the same as a male, in my opinion.
Thank you very much, Carla. Carmiño, I think you are.
I also agree with everything that Carla has said. I just wanted to, we haven't talked as much about mentors. And I think mentors are very important in a career. And I think that you need different mentors depending on the stage of your career. And I also would like to emphasize that it doesn't, if you're a female, it doesn't have to be a female mentor. You look for people, male or female, it doesn't, to me, it doesn't matter. It's more, does the person have, do you have an affinity with that person? Do they have integrity? Do they have knowledge that, and are they willing to share that knowledge? Because you could run into women who have worked so hard that they don't want to share, that they're not willing to help you. So really, so you want to find mentors at different stages in your life, more than one. And gender is not the only thing that determines whether or not that person can help you balance your mental health, your career goals, and also, I mean, again, at times, you may have more time and bandwidth to deal with more than there are other times, like if you're pregnant, where you have to deal with less. So life is complex. I mean, I'm sure we all know this. And there are no special specific formulas that are going to give you success. On the other hand, and then also, what is your definition of success? So all of this is part of that picture. And as you go through your lives and your professional lives, just keep it flexible. Keep yourself open to the opportunities. And if something doesn't work, then you pick up and move to the next one. And you try to integrate the lessons learned. Because you're right, none of us, especially those of us with the gray hair, we've had plenty of failures. I mean, I even mentioned I had to get out of Massachusetts. You don't even want to know what happened at that time. And I mean, my marriage fell apart. There many things fell apart. Anyhow, so you move forward. You know, life happens. You plan your career, and then life happens. And you have to take life with your career and somehow make it work. And it takes a whole village, not just women. It takes men, it takes women, it takes spouses, children to help us move forward. And anyway, I promise to be quiet now. Thank you again.
Okay, thank you very much, Carmina.
Me.
Yeah.
I agree with Carminia because for me, okay, I was so lost in the undergrad. I studied physics because I wanted to be a particle physicist. And then I was involved in 2 projects that never of them came, and it was so horrible. And I was like, what am I going to do right now? I need to write a thesis. And then a professor presented me a student who was studying the PhD in Universidad Católica de Chile, which I'm now today. And he was so passionate about this gamma ray burst. When he told me about that, I was like, I don't know how a person can talk like with this passion of this of a team. I want to be like him. And we started a project, and then the project was really good. And I had the opportunity to travel to South Korea to present my work in the General Assembly of the International Astronomical Union. And then I meet a lot of girls that they were astronomers, really a variety of girls. They were mainly from Latin America, from Argentina, Brazil, Chile, Guatemala, Mexico. And I was like shocked because I never found that maybe because in the undergrad we had a lot of professors, male professors, only 2 women. But the thing was that they were my age, so different and so passionate also about science. And I was like, oh, and I really need to pursue my career, but in astronomy now. And it's really inspiring how these events or like to talk with passionate people can reach us to the point where we are today. So I think mentors and real people are really important in life because in our careers, the critical thinking make us to choose different pathways. And the life experience we have through that and the narratives we have then are really important to share with people so they can understand that is doable. It's something that, yeah, we achieve this, but you can also achieve not in the same path, but different, but you are going to be able to do that because you have this critical thinking that science is providing to you. Basically.
Okay, I have another question. Franson, could you talk about imposter syndrome in women's team, and have you ever experienced it, and how did you deal with that? It's open to any of you.
Anna, I did not understand the question well enough. Could you repeat it, please?
Oh, yeah, sorry. Could you talk about the imposter syndrome in women involved in science, and have you ever experienced it, and how did you deal with that?
Well, I have had that several times. I think that everyone here has faced this imposter syndrome, which is kind of believing that you are where you are because of lucky or because they didn't find anyone else or because of I don't know what. So you feel like an imposter, like a fraud, you know? So at least for me, this has happened several times. I have found also that a lot of male that have my same age also have the same, and especially male that have families. So then it becomes, I don't know, I'm not sure if this is like gender related or parenting related or what, or both. I don't know. And what I try to do all the time, well, after a lot of therapy, I learned how to take care of my own thoughts, you know, because people can reinforce you, okay, no, you are good, you are great, look at what you have achieved and whatever, which is true and is helpful. But at the end, we need to control our own thoughts and believe ourselves what we have achieved and why. because if you don't have this process of healing, well, you will face this over and over again, and it won't get better. So in that sense, my advice will be that, well, heal whatever you need to heal, and try to control and to talk to yourself about the reality, and know what is going on in your mind, catastrophizing things that are not real at the end. I mean, there are some studies in neurology field that say that the brain at the end responds 90% to the unconscious stuff than the conscious part of the reality that you see. So it's very important to how you speak to yourself, because you will believe that. And if you speak wrong to yourself, but you will believe that too. That will be my advice.
Thank you very much for your insight, Carla. I don't know if someone has something else to say about related question.
I want to say, I'm laughing because
Please.
I thought, well, by now at this age, I am not going to. And just a few weeks ago, a person called me if I wanted to become an expert witness in a very litigious patent dispute between, and I can't give details, between a big manufacturer of telephone lenses for telephones and some other company, and this is millions of dollars that they're arguing about. And so I haven't done any lens design for a while. And I said to my husband, why do they think I have anything to offer? And I mean, they must be desperate to get somebody. Anyway, I ended up turning it down because also at this age, I know what my strengths are, and I know where I can make a difference, and where if I just let my ego run, I won't do a good job. So I turned it down. But that imposter syndrome really, I mean, I'm 65, and I thought, geez, I thought by now I wouldn't have it. And so anyhow, I think it's all right to have it, but you learn, as Carla, all of you have said, you learn what are your strengths. You learn, no, this is for me, no, this is not for me. And as you get older, maybe it won't take you 3 days to get over the fact that you don't think you're good enough. Now it only takes you 3 hours, and someday it will be 3 minutes when you're 90 years old. It doesn't matter. It's part of our humanity, and we embrace it and we work with it and we just move forward. So I wish I could say that it goes away. I was totally surprised. It just happened a few weeks ago, and I couldn't believe that I was back to having those feelings. And then after I settled, did a little meditation, I thought, okay, let's really put this around. Anyway, so that's how it goes. Some people are much more advanced at an earlier age. I am a little slow, so so I still have them. Anyway, thank you.
Okay, thank you very much to our speakers for their insights about this such an important issue. Because of the time, I'm going to finish the event. Well, I think like the lesson that we have from this little conversation is that, well, we have to believe it, to believe in ourselves, and to keep working our way up to whatever we want to achieve, because as you said, Carmina, the definition of success is different for everyone. So thank you very much for attending. In closing, I would like to highlight the importance and impact that these kind of initiatives have on our environment and society. Today, we have heard inspiring talks where female researchers from various fields share their experiences and knowledge, demonstrating the fundamental role that women and girls play in the advancement of science and technology. Today, we are reminded that talent and the ability to contribute to scientific progress know no gender or age. It is vital that we continue to promote the participation of women and girls in STEAM, removing barriers and fostering an inclusive environment where all can thrive. We thank you all once again, or all of our speakers for their participation. May their impressive work continue to inspire this and the generations to come. Thanks to the attendees for your active participation in this significant day, and let us move forward united in our purpose to make the world of science a more inclusive and diverse place for all. Thank you very much.